So the statement of the theorem is, let L be an n-dimensional lattice in Rn with fundamental domain T, and let X be a bounded, symmetric, convex subset of Rn. If volume of X is greater than 2 power n volume of T, then X contains a non-zero point of L. Okay, so now we will prove this theorem. So it is given that L is a n-dimensional lattice in Rn. So let E1, E2, etc., En be a set of generators of L. So they are generators of the lattice L. Now we consider another lattice with generators whose generators are 2E1, 2E2, etc., 2En. Now suppose that this generates another lattice and we denote that lattice by 2L. And its fundamental domain, we denote its fundamental domain. So fundamental domain of this lattice 2L, we will denote it by 2T. So since there are n elements in the generator set, we can say that dimension of 2L, dimension of this lattice 2L is n. Now we will find the volume of this. So volume of 2T. So by formula, it is integral dy1, dy2, etc., dyn in 2T. Now where the element y1, y2, etc., yn is an element of 2T. Now we can denote yi to be 2xi. So then x1, x2, etc., xn as an element of T. So now volume of 2T can be written as volume of 2T becomes, so we substitute for each yi as 2xi. So 2 raised to n can be taken outside the integral sign over T, and this becomes dx1, dx2, etc., dxn. Now by definition, this is 2 raised to n into volume of T. So we got that volume of 2T is equal to 2 raised to n volume of T. Now 2L is an n-dimensional lattice in Rn. So we have the dimension of 2L is n. So since 2L is an n-dimensional lattice, then n-dimensional lattice in Rn. So we can write Rn by 2L is isomorphic to the n-dimensional torus Tn. Okay. Also we have the mapping. We have the mapping mu. Mu is a mapping from Rn to Tn. We know that this is an onto homomorphism. Onto homomorphism. Also, we know that if we restrict this map to the fundamental domain, it becomes a bijection. So we denote it by phi. So phi from 2t is the fundamental domain here to Tn. If we restrict this mapping to to T, this become a bijection. So now this is a bijection. Now we will see what is volume of Tn, the n-dimensional torus Tm. So to find volume of Tn, by the definition, we have to find the volume of its inverse image. So it is volume of phi inverse of Tn. Now since phi is a bijection, we have phi inverse of Tn will be 2t. Okay, so phi inverse of Tn will be 2t because it is a bijection. So here we will get this is equal to volume of 2t. And here we have shown that volume of 2t. We have shown that volume of 2t equal to 2 raised to n volume of t. So we can substitute it here. So this becomes 2 raised to n volume of t. So we got volume of the n-dimensional torus Tn is equal to 2 raised to n volume of t. Now we have in the theorem we have mentioned that X is a bounded subset. So X is a bounded subset in Rn. Also the mapping mu is from Rn to Tn. So from this we can say that the image of this set is also, that is mu of X, is contained in or equal to Tn. Now if we take volume of this, so we get volume of mu of X will be less than or equal to volume of t raised to n. Now we already got here, we got that volume of t raised to n is 2 raised to n volume of t. So this is equal to 2 raised to n volume of t. But in the statement of the theorem, it is given that in the statement of the theorem, we have that 2 raised to n volume of t is less than volume of x. So applying this, we get, this implies volume of mu of x is less than volume of x. So we got that volume of mu of x is less than volume of x, which implies that volume of mu of x is not equal to volume of x, which simply means that mu is not volume preserving. Mu is not volume preserving. So if mu is not volume preserving, we can apply the theorem 6.7 and we get that mu restricted to x is not injective. So by that theorem, we will get mu restricted to x is not injective. This is not injective. So if mu restricted to x is not injective, it means that there exists. So there exists x1, x2, x1, x2 in X such that x1 is not equal to x2 but their images are equal. So, but nu of x1 is equal to nu of x2. That is, we have nu of x1 is equal to nu of x2. Now this implies that x1 plus 2l is equal to x2 plus 2l, which implies x1 minus x2 is an element of 2l, which implies x1 minus x2 by 2 is an element of L. So we got a non-zero element of L. This is non-zero because we have that x1 is not equal to x2. So this implies that x1 minus x2 by 2 is a non-zero element of L. Element of L. Now to prove the theorem, it remains us to show that this is an element of X. Now we already have that x1 and x2 are element of X, and we have that X is symmetric. Since X is symmetric, this implies x1 and minus x2 is also an element of X. Also, we have that X is a convex set. So, this implies half x1 plus 1 minus half x2. 1 minus half minus x2 is also an element of X. So, we got this since X is convex. We have used the definition of convex set by taking lambda equal to half. So, half x1 plus 1 minus half of minus x2 element of capital X. This implies x1 minus x2 by 2 is an element of capital X. So, it means that X contains a non-zero element of lattice L. So, that is X contains a non-zero element of lattice L. So we have proved the Minkowskis theorem, which says that if volume of X is greater than 2 power n volume of T, then X contains a non-zero element of L. So we have produced, this is that non-zero element which is in X, and it is also an element of L. Okay. So hence the proof of Minkowskis theorem.